All right, Physical Science 20. This is section 14.5 in your Heath Physics text, page 443. Should you want to go there? Ladies, hello. Thank you. The show's up here. Right on. Let's get through the notes here, and I want to talk to you about something very important, which is the equation for curved mirrors. We've talked about ray diagrams that we just got finished talking about, and we do want to be able to take an analytical approach to finding distances and heights of images and things like that. Okay? So ray diagrams are useful for figuring out where an image will appear, also for determining the important characteristics, right? Like size and position and orientation and reality. Those ones, you can comment on that. And over here on the right, we have a ray diagram, okay? So how did we find this image over here? Just as a refresher, we drew 3 rays, or at least 2 if we can, and from the tip of the object, we go parallel. Let's pretend that's parallel. And then it reflects through the what? Center? No, it's focus, right. Yes. You are absolutely correct. And the other one is through the focus till it hits the mirror, which that's not a straight line. And then it will reflect parallel. So those are really kind of almost one and the same, right? Yes. All right. So where these two meet will be the tip of the image. If the object was suspended in air, like above this imaginary principal axis, then you'd have to go from the bottom to and find out where the bottom was. So you do the same thing, which we haven't done an example like that. But if the object sits on the principal axis, the image will sit on that principal axis as well. All right. So that's great. And if we wanted to find, let's say we wanted to find the exact distance of the image from the mirror. Well, we could do a very carefully drawn ray diagram, which you will be doing. With a ruler, right? And you'll be measuring millimeters and how far. So you could do it that way, but there's also a mathematical relationship that we can use to determine distances and of things as well. So the mirror equation is something that's pretty important. We're going to be using this a lot. Is an equation that works for both converging and diverging mirrors. So here is the mirror equation. It is 1 over the distance of the object plus 1 over the distance of the image equals 1 over f. Who remembers what f is? Focal length. Oh, very good. You guys were paying attention. Nice work. Okay, so in red over here then, the distance of the object would be the distance from the object to the mirror. Now we would measure from, along the principal axis if we can, because who knows how this mirror is going to curve in, right? But we'll go from the principal axis to the mirror. And the distance of the image then, I should label that DO, the distance of the image, of course, is going to be this, the distance from the image all the way to the mirror. And the focal length, you are correct, is from F to V. Okay, that's the focal length. All right. Okay, well, why is it put over 1? Okay, that's good. We're not simply adding, okay. So look at this. Let's talk about that for a second. So if we didn't have these over 1, okay, would this make any sense at all? Right? F is smaller, in this case for sure, which would be in many cases, F is much smaller than both the distance of the object and the distance of the image. So it wouldn't make sense to add them up to get to F. So that doesn't work. What about if we subtracted? Well, it just so happens that subtracting doesn't work either. And when we come to these equations, right? There's a lot of experimentation. There's a lot of measurements. Patterns are recognized, and you come up with sort of a relationship between as many variables as possible, and then you get to form this equation. So it just so happens that when all of the relationships between objects and images and things like that, when it all comes together, if you take enough data at once, you start to see these patterns emerging. And it just so happens that the reciprocal of these when added will give you 1 over f. Okay? So if you want to dig deeper into the origin of the mirror equation, I would encourage you to do that. We're not going to get too far into that in the lesson, but it's a good question. So why is it like this? Well, why is any equation like it is? It's because of patterns that are recognized and formalized in mathematical quantitative ways, patterns of just things that we see, observations. Okay. All right, so pretty straightforward as long as you know what everything is. We'll do some examples here a little bit later. But in order for the equation to work properly, we need to make sure that we are using the correct, and are there any blanks that I've missed there for that one? We need to make sure that we're using the correct signs, okay? So that is plus or minus. So this is important. That's another thing we need to consider. The rules for the use of signs is called sign convention. All right, so convention is a blank, right on. Okay, so sign conventions. So they are, all distances are measured from the vertex of a curved mirror. So as I mentioned, we won't take it from the top of the mirror where the mirror curves in. We'll try and measure from the vertex of the mirror. Distances of real objects and images are positive. So that's really important. So the real objects, that is anything in front of the mirror. That could be real objects or real images. They're always positive. Okay, so a positive distance in the real territory. That should make sense. Distances of virtual objects and images are negative. So anything behind the mirror is negative. And maybe just over here, I'll just draw just something simple. So here's V, here's F, and here's C. So we have distance is positive on this side of the mirror, okay, on the real side. And distance is negative over here. Okay, negative over here. If that even helps. Can you see that? Okay. So object heights. Okay, what about object heights? Well, object heights are positive when measured upward. So heights are positive when measured upward, and they are negative when measured downward or in the inverted position. Okay? So anything, either object or image, if it starts inverted, let's say an object starts inverted, you have to use that as a negative height because this equation will give you, in this case, it might give you a positive height for the image, and you know that the image is upright then. So anything that's upright is positive, anything that's inverted is negative. What's the M? Good question. That's next. That's what I'm going to talk about right now. Okay. Any questions though about those signs? No, sir. Did I hear no, sir? Very nice. Very nice. Okay. All right. The M. Okay. Magnification. So we talked a little bit about magnification already when we talked about the pinhole camera. So the M is magnification, and we actually come up with a new equation given the what we know about our diagrams here now. So magnification, it would be found by relating the height of the image divided by height of the object. Remember the pinhole camera. Okay. What about distances? Okay, what about distances? Well, distances work too. There's a relationship between distances, but because of the sign convention, we have to be careful about how we kind of relate things here now. So if you're taking distances only, all right, distances only, then you're going to want to have a negative there in front of one of them. It doesn't matter if it's the image or the object, okay? I know that height can be up or down, inverted, but distances for magnification, you're gonna often have distances that are negative. So we can't have a negative on both of these. This is not, it's not easy to explain what happens when you take these separately. It is a little bit easier to understand when you take these together. So this is the magnification sort of equation that is expanded. So again, from the pinhole camera, the height of the image over the height of the object is the same ratio as the distance of the image over the distance of the object. However, if you put all of these together, then either something is going to be upright and inverted, or something is going to be up behind the mirror and in front of the mirror. So we have to account for all that. And when we include the signs now, this is the relationship that we have to have a negative in there somewhere. Okay? So the magnification equation works when we have a negative here. So if you have, let's say, height of the image, height of the object, and you have distance of the object, okay? If you put all that together to find DI, you would find that without this negative, it would tell you that it's incorrectly real or incorrectly virtual. So you have to have the negative in there to make sure that everything fits together. Okay, so here's a picture of the pinhole camera, and this is not exactly like a mirror situation, obviously, because the light goes through, it does not reflect back. This would be more like a lens situation, which we're going to talk about lenses next. But think about this. If this distance here, DO, okay, if that's positive and this is positive, the height then, well, one would have to be up and one would have to be down, okay? So if they're all positive, they can't possibly all be positive. If you look at some of your, some of your diagrams, okay, for the, well, where is it? Ray diagrams. Okay, that's not it. Ray diagrams here. Okay, so ray diagrams here. Okay, so object and image, okay, if they're both real, so distances are both positive, then the object and the image are, one is up, one is down, okay? This one over here, if they're both inverted, both upright, you see how the object is up here, facing up, and the image is facing up as well. If they're both upright, then one has a negative distance. You see that? You'll never have positive distance of object, positive distance of image, and they're both being upright, so both positive heights. You never have that. So that's the whole point. So if we're going to do the equation properly, we have to make sure that there's a negative sign in there somewhere. Okay? All right, I am going to do spherical aberration here as well. I'm going to give you a chance to do some questions here, but I'm going to do sort of these two sections at once. So any questions, first of all, about the equation or the sign convention? And I know you haven't done the actual practice yet. I appreciate that. So you might have some questions later. But anything on what we've talked about so far? Okay, we will get some practice with this, I promise. And those will be those questions. But let me talk to you about spherical aberration before we get into doing those questions. So spherical aberration, the rules that we have covered for diverging and converging mirrors do not work if the mirror is too large compared to the radius of the mirror. So think about a curved mirror. If we have a center of curvature, that would mean the mirror is literally a part of a circle, right? A center. So if we consider mirrors that are not too big and that only curve slightly, then we're good. But if this mirror curves around like this, notice how, look at the mirror, if it was a complete circle or a large part of a circle, would actually curve back on itself. So obviously if we have some kind of image down here, that's not going to work, right? It's not even going to get to the mirror. So we have problems if the mirror is too circular, too big. Okay? So what happens if we use mirrors that are too large? We get something happening called spherical aberration. So spherical refers to a sphere or a circle or a ball, three-dimensional, like a ball or a circle. And aberration would be the word that would be like not expected. The results would be not expected. They would be off a little bit. Okay, it's an aberration. It's like an error or a mistake, or it's off what is to be expected. All right. Now, what do you have in your notes here? Just give me a second. So you have that diagram. It's maybe a little tough to see, but what about some blanks here? Too large. Yeah, large is a blank. Okay. Compared to the radius of the mirror. Beauty. All right. So to understand this, why this happens, look at the image here below or beside in my case. So if we have a light ray, okay, that's coming in here, let's say pretty close to the principal axis, it should reflect through the focus. This one too should reflect through the focus. But as we get further and further out, so this light ray, these light rays, and this one for sure over here, the reflection is not going to go through the principal focus, but it's going to be a little aberrant. Okay, this one is going to go down, it's going to go down here, away from this focus, and this one for sure is going to come way over here. So we have problems, okay? If the mirror is too large and too much of a curve, then the image is going to be unclear. Okay, it'll be really fuzzy on the edges, the top and the bottom of the image, let's say. Okay. So each ray strikes the mirror. They all have their own angle of incidence and angle of reflection, as we know. You can see that as you go further away from the principal axis, the angles of reflection stop hitting the focal point. So here's on your notes, you have these two diagrams as well, which really helps explain and show what happens here. So a spherical mirror that is literally a part of a circle like this will have much spherical aberration when the light rays hit the outer edges of the mirror. That's why we use parabolic, okay, mirrors, because they aren't actually spheres, they're closer to parabolas. So here would be sort of more of a spherical shape, and here's a parabolic shape. So the parabolas account for the spherical aberration. So what do the notes say? Because this happens in spherical mirrors, we call it spherical aberration. Aberration means deviation from what's expected. To keep this from happening, engineers and physicists must use parabolic mirrors instead of spherical mirrors when designing large projects that rely on mirrors. Okay? And that's the end of that short little section there. Spherical aberration. Okay, any questions about spherical aberration? All right. So just a note in chapter 14 as well, because this is from chapter 14, there are notes on applications of curved mirrors as well. I would like you to look through those. Remember, I may be giving you a quiz on these applications, so you should read them and study them. The optional notes are optional, but you may have your notes for any quiz that I might give you on any applications. So I would encourage you to read through, study, make your own notes on the applications. Plus, all the interesting engineering and scientific applicative aspects of science come in these examples. So yeah, they are kind of neat, and this is where science leads, right? All right, so we'll save 15.1. This is the end of chapter 14 here. You do have a chapter 14 review assignment that will be up, and that should be right here. Here's all your the unit 4 work. So the chapter 14, and here's your questions from chapter 14. So this is what you should have. This is what you should have in your sites here so far. So all these questions here that we've worked with in class. Okay, I'll just get you going on the first one. Number 1 says, determine the image distance. Okay, so you want to write down the image distance. It's the distance of the image we don't know. Okay, in each of the following situations. So A is a converging mirror. Might be a good idea to sketch a little diagram somewhere. That might be a good idea. Converging mirror. So that's one where the rays all converge to a focal point in front of the mirror. So got a situation like this where it has a focal length of 15. Okay, so this is 15 centimeters, right, from F to V. That's 15. The object is placed 40 centimeters from the mirror. So let's do that one first. So in your diagram, it might be a good idea to place the center here. And how far is the center from the mirror? Sorry? 40. No, the center is 30 because it's double the focus. The center. The object is 40. Okay? So the object is 40. So we know it's going to be just a little bit beyond here. So let's put our object right there. All right? So a little diagram might give us some indication of how we should use our sign convention, maybe, right? So let's see. What are we trying to find out? DI. Do we have DO? Yes. Yeah, we do. DO is 40 centimeters. Okay, excellent. And do we have F? Because that would be really nice to have so we could use our new equation that we just learned. And F is what? 15. Okay. So what is it? 1 over what? What's our equation again? DO, DI, and F, right? DO, DI, and F. And you could do dido, do-di. Dido is easy to remember. So once you do, it's adding, you can put them in any order. Dido, right? 1 over di plus 1 over do equals 1 over F. However you want to remember that, this is our formula. So let's plug in what we have. We have DO and we have F. So this is going to be 1 over DI plus 1 over 40 equals 1 over 15. Now, to isolate DI, right now it's in the denominator So we'll deal with that in a bit, but let's get this whole term by itself on one side. So let's subtract 1 over 40 from both sides. You can do this on your calculator. You can do this manually. It doesn't really matter. But you have 1 over di. You have to have a common denominator here, right? If you're going to be doing this manually. Some of you in your calculator, and you can use your calculator for this, that's fine. Some of you should have a fraction button. Actually, I don't really do this much on this calculator, so I don't know, I can see. But if you did 1 over 15, okay, minus 1 divided by 40, okay, so you get that decimal. Now I think I could go to fraction there and see what it does. There we go, 1 over 24. So your calculator might be a little bit easier to navigate there. But you get a common denominator, okay? So you could simply multiply these together to get a common denominator and then multiply the tops by the appropriate numbers and subtract and simplify. It comes down to 1 over 24, all right? So adding fractions is not the subject of this lesson, but if you need help with that, come talk to me or get some help with that for sure. But here's the thing, when you get to this point, okay, 1 over something has to equal 1 over 24. So it's pretty easy to see that these two fractions have to be equal. Therefore, di must equal 24. Di must equal 24. So the distance of the image, okay, so where did my, I had stuff disappear here. 1 over 24 comes from subtracting those two. Okay, I can come back to that if you need help with your calculator or whatever. But when you get this point, remember, you can take the reciprocal of both sides, and you definitely want your di, what you're trying to solve for, you want it by itself and in the numerator, okay, on the top. So you flip both sides, then you can see the di equals 24. So here's our object over here at 40, and this is 30, so 24 is going to be down here. And do you think it's going to be upright, or is it going to be inverted? Yeah. Oh, sorry, what did I hear? Inverted, yeah. Again, parallel, focus, focus, parallel, inverted. And the exact distance would be 24 centimeters. Make sure that your units line up there, okay? So that's 1A. Now, if we're trying to find the height, of the image, you would need to know either the height of the object. You need to know the height of the object. So, okay. Yeah. Any questions about that? So number 2, again, I'll say that again. By means of a scale diagram, locate the image and determine its height. So you have to draw with your ruler. You have to draw the principal axis. Guys, listen for a second. When you're doing scale diagrams, you can draw just straight lines at a 90 degree to the parallel or to the principal axis. Draw a straight line. What I would suggest you do, if it's a converging mirror, which in number 2 it's a converging mirror, I would just show that by just curving the edges, okay? And you can put your little hatch marks behind there if you want. But here's your object or whatever. Use a straight line because you're going to use a ruler and you're going to measure things exactly to the millimeter, and you're going to draw your lines and so on. So it can be to scale. If it says 30 centimeters, you don't have, your sheet is not 30 centimeters, so you're going to have to draw to scale. So do half, or do a third maybe, or do a quarter, okay? So draw to scale. And if you need help with drawing to scale, you can ask. But it basically means by an exact to scale ray diagram, follow all the rules, draw straight lines, and determine the height. Locate the image, determine its height. When it says locate, you need distance of image and height as well. Okay, so scale ray diagram for number 2. Okay, so here's your answers for number 1. Okay, just to double check that you've got everything correct here. We did this A together. So 24 centimeters should be the distance of the image for A. For the second part, you should have a distance of negative 30. So again, that is behind the mirror, right? Because it's negative. B should be first part negative 6.7 and the second part negative 12.
1A is 60. What did you divide by? 6. I did.